Our next topic is looking at something called antiderivatives, or another way to say it is indefinite integration. And when we're looking at these ideas, it is trying to go backwards on the differentiation process. So what we're asked to find the antiderivative of, or the indefinite integral of, is really what is the derivative of an original function. So we need to find out what function has that as its derivative. Now, when we think about our differentiation process, we need to make sure that we review them and we're really comfortable what we did when we differentiated so that we can have some hindsight for our path back. I also want to remind you that anytime we had a function that had a constant term and we differentiated it, the constant term's derivative is 0. So when we're integrating, finding the antiderivative, we need to make sure that we allow for that constant term to have been there. And so we need to always remember to put plus c for plus a constant in case the original function had that. So when we're actually finding our antiderivative, we are looking at a family of functions as the answer to that specific question. Now, think about these particular derivatives that I want us to recall, and there's a lot more that we're going to deal with. I just wanted to start with these examples. So remember, the derivative with respect to x of a number, that as a term is 0. The derivative with respect to x of x is 1. The derivative with respect to x of x to a number power is bring down the number power, keep the base of x, and subtract 1 from the exponent. The derivative with respect to x of sine x is cosine x. The derivative with respect to cosine x is negative sine x. The derivative with respect to x of secant x is secant x tangent x. And the derivative with respect to x of tangent x is secant squared x. So what I'd like to do is just start with those and then show the notation of how a question is presented to you, asking you to do this antiderivative process or find this indefinite integral, and then we'll list a few more. So first let's look at what if they're asking me to find the antiderivative or the indefinite integral of 0. Well, how are they going to ask us that question? To ask us the question, the notation starts with an elongated looking sort of S, that's called the integral sign, and then what they're asking us to integrate, and then the variable of which we are our integration process with respect to. So here I want to go backwards on what if I had 0 as my derivative here, and then it's with respect to x. So what function has 0 as its derivative? Well, c is what had 0 as its derivative. Let's look at the next one. This one I had 1 as the derivative. So to go backwards on it, I'd say the integral sign, my 1, and then with respect to x. So that tells me what variable to use when I'm going with the finding the indefinite integral. So then what function using the variable x had 1 as its derivative? Well, that is x, but I have to allow that there might have been a constant term. So I write plus c. Next is the integral of x to a number power with respect to x, where my number power is not -1. Now this one doesn't match up exactly with the notation, but the thought process is what we want to use. So when I was differentiating a letter base to a number power, I brought down the exponent, kept the base, and subtracted 1 from it. So now to go backwards on that, to get from nx to the n minus 1 back to the x to the n, I would need to add 1 to the exponent, because n minus 1 plus 1 would just give me an exponent of n, which is what I have in the bracket here. So I would have to add 1 to the exponent, And then once I have that power of n on there, I still need to undo that multiplication by the original exponent. And so to undo that multiplication, I have to divide by that n plus 1. And then remember, my plus c is a constant term. Now this could be written in either the way where I divide by the n plus 1, or if I have the fraction 1 over n plus 1 in the front. And it kind of depends on the specific question that you're doing to which way you want to write it. Now here, the integral of cosine x dx, what function has the cosine x as its derivative? Well, the function that had the cosine x as its derivative is the sine of x. And again, remember your constant c. Now this next one would be if I have the integral of sine x dx. Well, if the derivative of cosine x is negative sine x, then the function that would have just regular sine x as its derivative would be negative cosine x. And then plus my constant term. Now these next two I wanted to put on there because they are a little bit trickier when you're looking at them, unless you really have it strong in your memory that they were derivatives that came from a specific trig function. And the reason I say that is because the derivative with respect to x of secant x is actually the product of secant x and tangent x that came out of the derivative. So when I see this integral of secant x tangent x, that just goes back to the trig function secant x. So the integral of secant x tangent x dx is equal to secant x, and then plus c. And then our last one here, that the derivative with respect to x of tangent x is secant squared x. So if I'm finding the integral of secant squared x dx, then I would get tangent x plus c. So I guess the thing you have to be careful about here is that there will be other times where there will be multiplications that I either have to carry out if they're a polynomial times a polynomial, or there might even be other situations where I'm going to go backwards on the chain rule later down the line when we get into something called U substitutions. And I might need to use a little bit fancier techniques to work with those problems. And I need to recognize when it needs something a little bit more involved, as opposed to when it's just actually something that was a derivative of original function and I can just work my way back. So when I see the integral of secant x tangent x dx, that looks like, oh my gosh, I've got a multiplication there, I've got to be careful of how I work with that. But this particular multiplication of secant x tangent x actually was a derivative of secant x. So there's not any real fancy stuff that has to occur here. I just have to make sure that I'm very comfortable that secant x was the function that had that as its derivative. Now each time we write these, we need to make sure with an integral question we have these components. You have the integral sign, and then you have the notation that tells you with respect to which variable you're integrating. And then this expression that you are integrating is called the integrand. And the integrand has to be sandwiched between the integral sign and the notation of what variable you're integrating with respect to. Okay, so now with these, there's also a property that says if you're integrating a function f of x plus or minus a function g of x with respect to x, that you can integrate them term by term. So this is the integral of f of x dx plus or minus the integral of g of x dx. So I can do term-by-term integration. And then also, the integral of a constant k times a function f of x dx is equal to, you can pull the constant factors out in front of the integral. So it's equal to k times the integral of f of x dx. So those properties will help us a great deal when we are working with our specific examples. Now I'm going to do one example here, and then we'll look at some other examples later on. So for example, let's say we have find the integral of 2x minus 3 to the second power dx. Well, I don't have anything so far at my disposal with just these basic integrals and just these basic properties to go backwards if I have an action on an expression. So what I need to do at this point of the discussion of it is actually multiply out this binomial so that I get it to be term by term. So we are going to still have the integral, and when you multiply out 2x minus 3 times 2x minus 3, you get 4x squared minus 12x plus 9. And now I have it where it is term by term, and so I can think of each of those integrals separately. So it's the integral of 4x squared dx, then minus the integral 12x dx, and then plus the integral of 9 dx. Now with each of these I could actually factor out the constant in front of the integral as we go from one to the next. So I have 4 times the integral x squared dx minus 12 times the integral x dx, and then plus 9 times the integral 1 dx. And as we get further along and we do more of these, we'll just think that through instead of writing out the specific steps. But at this point, it just helps to show that we are only using our basic properties and our basic integrals from the very beginning of the differentiation process. Those are the ones we're going backwards on. Okay, now it's 4 times, you can multiply 4 times what you get for the integral of x squared dx. Well, that's a letter base to a number power, and to integrate those, we add 1 to the exponent and divide by that. So x to the 2 plus 1 is third power, and I'm going to divide by 3. So when I divide by 3, I'll have a coefficient of 4/3. So I could divide it under the x, or I could have it as the coefficient out in front. Okay, then minus, this is the integral of x to the first dx. So I have my x, 1 plus 1 is 2, and then divide by 2. So take that 12 and divide it by 2, and you get 6. And then for the last one, I have plus 9 times the integral of 1 dx. What function had 1 as its derivative in the variable x? Well, x is the function that had 1 as its derivative, so that's going to be 9 times x. And then I have to remember plus c, my constant term. And you don't need a plus c for each of the individual terms that you get. They'll all accumulate at the end, so you can just have the plus c at the very end. So I've started out by rewriting a lot of the indefinite integrals that we have from our basic work down, and it might be something that you'd want to do to write a dedicated page that lists out the indefinite integrals of basic functions. So remember, our integral of 0 dx is just the constant c. The integral of 1 dx could also be written where it's just the integral and the dx, and the 1 is assumed there, and that goes back to x plus c. Now, I did take a line here to write that the integral of x dx is 1/2 x squared plus c, just because a lot of times it's easy to forget that's an exponent of 1 and get stuck on that, so I wrote it as a separate line, but really it's embedded within this general case. And then our integral of x to the n dx, as long as your exponent's not -1, then that's 1 over n plus 1 times x to the n plus 1. So remember, add 1 to the exponent and divide by that. On the first screen, I put it underneath the x. On this one, I wrote it as a fraction in front, as a coefficient, and it really depends on what the format of the term you're working with to which one would be easier to think through, and then plus c. Now, what if my exponent is -1? Well, then I can't add 1 to the exponent and divide by that, because -1 plus 1 is 0, and you can't divide by 0. So the only case of the integration with our letter base to number power that you don't use this general power process with is if your exponent is specifically -1. So if you try to integrate it by adding 1 to the exponent and dividing by that, and you end up trying to divide by 0, which you know you can't do, that's the reminder, or that's the cue that it goes back to the natural log of the absolute value of x, and then plus c. And again, that's for your letter base to your number power. Now your integral of cosine x dx is sine x plus c. Your integral of sine x dx is negative cosine x plus c. And then the ones that we talked about before, and I've added a couple. So the integral of e to the x dx is just e to the x plus c. Remember, e to the x was its own derivative, so it is its own integral as well. And then the integral of cosecant x cotangent x dx is negative cosecant x plus c, and the integral of cosecant squared x dx is negative cotangent x plus c.